All right, guys, there we got polynomial functions and their graphs. I'm going to be honest with you. There's a lot of stuff in this video, so it may take a couple minutes to get through this stuff. But you saw every bit of this in your Algebra 2 class. It's going to be a big time review, but there's a lot. So hang in there, take some notes, get what you need to get, and I don't know. Let's just go. All right. Some words here you need to make sure that you know. First one is leading coefficient. Leading coefficient is the coefficient on the leading term. Leading term does not mean it's the first term. It means it's the term with the biggest exponent. And the largest exponent is called the degree. This is degree 5. And the leading exponent, the leading coefficient would be 3. Okay, so again, these are polynomials in one variable today. And a polynomial cannot have negative exponents, cannot have x's in your denominator of a fraction, stuff like that. Coefficients, I think you know what that word means. Those are all the numbers in front of the variables. The constant term, the term usually at the end is with no x's. It's called the constant term because it's always the same. All right, continuous is a big deal. The graph of polynomials are continuous, which means there's no breaks, no holes, and no sharp turns. For example, these first two right here, this is not continuous because there's a break in it right there, and there's a hole. Okay, if there's a hole or break, it's not. This one is not continuous either because it has that, they call it a cusp or a corner where it's a sharp turn. This one is continuous. This is a graph of a polynomial function because it's smooth, continuous. Same thing here, smooth, continuous, it's a polynomial. So if it's a break or a cusp or a hole or a corner, not a polynomial. Sorry about that. Okay. This is huge right here as far as knowing what the graphs look like of polynomial functions. Look at y equals x. Y equals x, obviously goes through 0, 0, 1, 1, 2, 2, 3, 3. It's called the identity, and notice it's going down, left, and up, right. Look at x squared. X squared is a parabola, right? It's going up to the left, up to the right. It's x squared, though. Look at x cubed. X cubed is going down to the left, up to the right. X to the fourth is going up to the left, up to the right. X to the fifth, down to the left. If you notice, they have the same general shape, like the x squared, x to the fourth, same general shape. X to the fourth is a little bit steeper. X cubed, x to the fifth, same general shape. X fifth is a little bit steeper. Okay, so the odd functions, if it's an odd degree, pretty much going to have this one, this one, this one. Pretty much the same shape. Of course, this one's a little bit weird because it's a line. Down, left, upright. And the even ones are going to have basically the same shape. Okay, that's a big deal. Didn't mean to do that. Let me see what I want. Like 4 more slides. Okay, this one says sketch the graphs. Now, I'm just going to use the transformations that we learned earlier to draw these things. And this one says negative x cubed. Now, negative in the front, remember, reflects across the x-axis. So this one, instead of going up, right, and down, left, it's going to do just the opposite. And it would do just like that. That's what negative x cubed would look like. Okay, x to the fifth looks the same, have the same general shape, but there's some stuff going on here. It's got a plus 4, which means it's been moved up 4. The negative still means it's the shape's been reflected, so it's going to do this kind of deal. And it's going to kind of go, we'll try in here. It's going to go like this and like that. That's the x to the fifth. This one right here, I can't see the exponent. Let's say it's x to the fourth, just for fun. If that's x to the fourth, I'm going to go right 2 because of the minus 2 inside. I'm going to go right 2. X to the fourth is going to be really steep. It's going to go just like this. Okay, so it's a general shape of those 3 graphs right there. And again, graph those with not any work, just those transformations that we've always done. All right. A few things about end behavior. Important stuff here. This whole thing's important. You've seen almost all this before. Again, just a lot of it. Okay, so you need to know that symbol. If you see this symbol right here, it means x is going to positive infinity. It means the graph is going to the right, the x becoming large in a positive direction. If you see this symbol, it means it's going to the left. It's going to negative infinity. X becomes large in a negative direction. Okay, so this is going right. That's going left. Okay, so here's what we know. If you have an odd degree, the graph of it, and the leading coefficient is positive, hard to read that. Leading coefficient is positive, it's going to go down, left, up, right. That's what we saw in the first slide. And we're going to write it like this. I don't know if you can see that. Right here, obviously. Y is going up as x is going right. This is saying y is going down as x is going left. If it's odd and negative, then it's going to go up to the left and down to the right. And we would say it like this. As x is going to the right, y is going down. As x is going to the left, y is going up. Now, if it's even degree, if it's even, the ends are going to do the same. Either both going up or both going down. And here's how I write that. As x is going to the left, y is going up. As x is going to the right, y is going up. I'm going to blow this up a little bit so you can see it a little bit better. Okay, right here on this last one, y is going to down, negative infinity, as x is going left. This one, y is going to negative or down, negative infinity down, as x is going to positive infinity, which is right. Okay, so one more time. If it's odd positive always looks like this. Odd negative always looks like this. And by saying negative, I mean the leading coefficient. The degree is odd, leading coefficient's negative or positive. So on this one, if it's even and positive, it's going up. If it's even and negative, both ends go down. Okay, determine the end behavior of this one. So what I see is the degree is 4, leading coefficient's negative. So I'm thinking, okay, it's even degree, negative coefficient, which means it's going to go down both ends. So to describe that, we're going to say, okay, as x goes to left, the y, which we're going to call p of x is also going down. As x goes to the right, the y, or p of x, is going also down. If it's going up, of course, I put positive infinity instead of negative infinity. Right, zeros, big slide here. The real zeros of a polynomial, if p is a polynomial and c is real, then the following are equivalent. Okay, if c is a 0, then c is also a solution. Those are big deals. If c is a 0, c is a solution, and c is an x-intercept. Those three words all represent the same number. A 0, a solution, an x-intercept, all the same number. A factor would be x minus c. Okay, so let me just show you what I'm talking about here, but all those words mean the same thing. Let's take the polynomial I have written down here. If I were to set that equal to 0 and factor it, I would get x plus 3, x minus 2. Now, those right there are called factors. That is what number 3 says right there. Those are factors, right? Zeros would be negative 3 and 2. Those are zeros. Now, because they solve the equation, they're also solutions. Not only they're solutions in zeros, but they're also x-intercepts. If I were to graph this polynomial right there, it would cross the x-axis at negative 3 and 2. Those would be 2 points on the graph. So the graph, it may do something like this. It's a parabola for sure. It may do something like that, but it's going to cross the x-axis at those 2 points. So those two numbers, when you do that, factors are what you get when you factor. The two solutions you get are called zeros, they're called solutions, and they are called x-intercepts, all the same number. Okay, intermediate value theorem just says if you plug in a number, if you plug in a into a function and b into a function and they have opposite signs when you work it out, that means there's a 0 in between the two. It means there's an x-intercept. There's a solution in between those two numbers if you plug one in and get a positive and one in and get a negative. Okay, guidelines for graphing. We're going to graph some here in a second. To get zeros, factor to find all zeros, and they are x-intercepts. So find the zeros first, get your x-intercepts. Let's skip number 2 for a second. Go to end behavior. Find the degree and leading coefficients, figure out what the ends are doing. Test points. Make a table for values, include test points to determine what's going on. In between the x-intercepts, include the y-intercept in the table, and then graph it. Plot the points we have. So let's try a couple here. Okay, it says graph this thing right here. Graph and find the zeros of x cubed minus 2x squared minus x. Okay, to find the zeros, we're going to factor. So I'm going to say 0 equals, factor out the GCF, which is x. That leaves x squared minus 2x minus 3. Factor what you have in there still, you get x minus 3x plus 1. And so my zeros would be 0, 3, and negative 1. So I'm going to plot those. 0, 3, and negative 1. Those are my zeros. Those are my x-intercepts for sure. Now my y-intercept you can find just by plugging in 0 into your initial function. If I plug 0 in here, the y-intercept is 0, which I already have, obviously. I got a point at 0, 0. Now, also notice the degree was odd. Leading coefficient's negative, which means it's going to go down left, it's going to go down this way, it's going to go up this way. Now, in order for it to do that, it means it's going to go above the x-axis between those two zeros. It's going to go below the x-axis between those two. Now, for today, we're not real concerned as far as exactly how far up and how far, because we'd have to graph a bunch of points to get the exact graph. So for today, we're going to concentrate on what's going on between the x-intercepts. Is it going above the x-axis or below the x-axis? And you can tell that based on the end behavior. Try another one. Finding zeros. So again, finding zeros and sketch the graph. Okay, now this has got 4 terms. So you got to factor that by grouping. This is why I chose this one to kind of remind you grouping. So I'm going to group the first 2, take out the x squared. That leaves x minus 2. The second 2, I'm going to factor out a negative 4. That also leaves an x minus 2. And it's important that you get the same thing in those parentheses. So you have an x minus 2. If you pull out the x minus 2s, that leaves an x squared minus 4. If you factor x squared minus 4, you get x plus 2, x minus 2. So really I have this. Really I have x plus 2, and I have x minus 2 squared, and I should have had that equal to 0. So my zeros are negative 2 and positive 2, which is what I need. So it's going to cross the x-axis at negative 2 and also positive 2. Notice this was x cubed, though, which means it's odd and positive, which means that this is going down on this side. On the right side, it's going to go up. It's going to go up over here. Now, one weird thing about this one is that we haven't talked about yet, which is coming on the next slide, I think. If you have a factor that is squared, right, the exponent on a factor is called multiplicities. How many times, this is called 2 is a 0 of multiplicity 2, which means it happens twice. I could have written negative 2, 2, and 2 would be my zeros. It would be repetitive, but you could do that. But because it happened twice, what that means about the graph when it gets to the 2, that means the graph bounces there. It doesn't actually pass through. So the graph's going to look like this. It's going to pass through the negative 2, but when it gets to the 2, it's going to bounce. It's going to hit the x-axis and bounce back up, not actually pass through there. Okay, so when you have an even multiplicity or an even exponent on a 0 or on a factor, that's what's going to happen with the graph. Instead of passing through the x-axis at that point, it's going to bounce at that point. And sure enough, here's what happens. The shape of a graph near 0 with multiplicity m. If the multiplicity is odd, if the exponent is odd in the parentheses, basically the graph just passes right through C. It just passes right through. But if the multiplicity is even, right, meaning the exponent is even, the exponent is 2 or 4 or 6 or 8, the graph bounces. That's why a parabola bounces sometimes off the x-axis, because it's an even exponent. All right, graph this one. Now, this one's already factored for us, so I'm going to find my zeros. My zeros are 0 and 2 and negative 1. Now, 0 has multiplicity 4 because it has an even exponent. 2 has multiplicity 3, and negative 1 has multiplicity 2. Now, the even multiplicities, remember, the graph's going to bounce. So it's going to bounce at the 0 and negative 1. So I'm going to put a 0 here, a negative 1 there, a 2 there. Now, add up all your exponents, because that's what the degree is going to be. 4 and 3 is 7, 7 and 2 is 9. So it means it's odd. It's an odd degree and positive, which means it's going to go down left, up right. So I know it's going down left, starting down here. It's going to go to the negative 1. It's going to bounce at the negative 1 because it has an even multiplicity. It's going to go back down, but then it's going to come back up through 0. Now, as it goes back up, it's also going to bounce at 0 because it also has multiplicity that's even. It's multiplicity 4. And then it's going to go back down and then come back up through the 2. And it's actually going to pass through the 2 because the 2 has a multiplicity 3. Okay, that's not a very good looking graph, but it's representative of what happens because it's going to bounce at the 0, bounce at the negative 1, and actually pass through the 2 because it has an odd multiplicity. That's a mouthful. All right, almost done, guys. Hang in there. Next to last slide here. Local maxes and local mins. A polynomial member has smooth curves, no breaks, no gaps, no holes. If the very top of a hill on a graph is called a local maximum, at the very bottom of a hill or valley is called a local min. Okay, so it's what you would think. Now, here's what I need you to know about these. How many are there in a graph? Whatever your degree is of a polynomial, if it's degree n, the graph can have at most n minus 1. 1 less than that maxes or mins. So if you see an x cubed function, a cubic function, it can only have at most 2 maxes or mins in it. Like the picture you're looking at right now, that could be a cubic function because it can have at most 2. All right, if it's degree 5, it can have at most 4 maxes or mins. Local maxes, local mins. All right, let's just go through. This is the last slide. Part A, how many local extrema each polynomial has? How many it has? Well, that's how many it could have. Okay, first of all, because it's degree 4, this one could have at most 3. And we would graph it to find out exactly how many, but it could have at most 3. Part B could have at most 4. Have to graph it to find out how many it had. Part C have at most 3 maxes local. They're calling them extrema. Extrema stands for maximums and minimums. So you can just use that word to talk about both. All right, so a lot of stuff in that lesson. I mean, a lot, but you have seen whether you believe it or not, you've seen it all before. It's all review, but it's a lot of review. So we'll work on all that stuff tomorrow, knock it all out. Can't wait to see you. See you then.